Okay, hello everyone. In this presentation, I'm going to explain D flip-flop. So first of all, why it is named as D flip-flop? D stands for delay. I have written here delay flip-flop. But the next question is, why we need the D flip-flop? Because we have already studied the SR and the JK flip-flop. That means the set and the reset and the JK flip-flop. So why really we require the D flip-flop? Basically, D flip-flop is used if we want to take only set and reset state of the SR flip-flop. If you remember, in the SR flip-flop, there was one unused state when the S equals to 1 and R equals to 1. That means that state was the unused state. So if we just need the set and the reset state of the SR flip-flop, then we will use the D flip-flop. Is it clear to you? That means we don't require to use all the states of the flip-flop in SR. We just need the set and the reset state of the SR flip-flop. So there is no need to use the whole SR flip-flop. We will just use the D flip-flop. Now, what is D flip-flop? As I have told you, SR flip-flop. So this is basically the SR flip-flop. As you can see, there are 4 NAND gates, 1, 2, 3, 4, same the output Qn and the Qn bar. So the output is fed to the gate number 3 and the gate number 4 inputs, and this is the clock pulse. You all know the clock pulse must be high for the operation of the SR or any of the flip-flop, and then there is a NOT gate here. That means we have connected basically S and the R. Now these are not the 2 inputs. This is only the 1 input. Both are connected with the NOT gate. So if in exams it is asked that draw the D flip-flop with the NAND gates, so you can use this diagram, and in place of this inverter you can use this NAND gate. You all know the NAND gate is the NOT gate is replaced by a NAND gate using this configuration. Okay, so you can use the NAND gate here as an inverter. So this is basically the D flip-flop in which S and the R, both the inputs are connected with a NOT gate. Okay, so this is the gate diagram, and this is basically the block diagram, you can say. In the block diagram, you can see I have replaced these all 4 gates with a block. I can say it is a SR flip-flop here, and then this is the input here, and we have connected both the inputs with a NOT gate. This is a clock pulse. Clock pulse must be high for its successful operation, and this is the input delay, D flip-flop, and these two are the outputs Qn and the Qn bar. Okay, so why we use the delay flip-flop? If we just want to use the set and the reset state of the SR flip-flop, we use the delay flip-flop. Okay, and now you can see the characteristic table and the truth table of this delay flip-flop. Okay, so I will explain you in the last how to make this characteristic table and how to make this truth table. Okay, and now in this characteristic table you can see, like in the SR and the JK flip-flop, we have seen there was 3 inputs. So if there were 3 inputs, that means how many combinations are possible? You all know 3 inputs means 2 raised to the power 3 equals to 8 combinations. So we have made the 8 states there. But here in the D flip-flop, how many combinations? Because there are only how many inputs? 2 inputs. So if there are 2 inputs, that means how many possible combinations will be there? It will be 2 raised to the power 2 equals to 4 combinations. So these are the 4 combinations: 0 0, 0 1, 1 0 and 1 1. Okay, so we have to determine here the next state, as in all of the flip-flops we have done. Okay, now we can again find the Qn plus 1, as in all of the flip-flops we have find out, like Qn plus 1. We have to find this Qn plus 1 here. Okay, so Qn plus 1 will be, what will be Qn plus 1? We will take two cases now. If D equals to 0, so we have applied D equals to 0 here. Okay, we applied D equals to 0. I will explain you in the next slide. In the next slide I have made like now this will be clear to you. In this one, as you can see, when D equals to 0, when D equals to 0, you all know the truth table of the NAND gate. That NAND gate truth table is given to you here. So if D equals to 0, that means this 0 is going here. Okay, and this is the NOT gate. So if this is 0, that means 1 will be here. Okay, so we will solve this gate first because this input is 0 here. So if 0 is given to the NAND gate, what will be the output? The output will be 1 here. Okay, and what will be the output here? Because both of the inputs are 1, the output will be 0 here. Okay, so I have written here, if the output is 0, that means we can solve this gate easily here. So 0, if one of the input of the NAND gate is 0, that means the output is 1. So this 1 is feedback here. So 1 into 1 equals to 0. That means we are getting the same output as we have assumed the input. That means if Qn plus 1 equals to Qn. Okay, you can easily solve it. And when D equals to 1, here, we can use this NAND gate configuration as an inverter here. D equals to 1, that means 1 is going here and this 0 is going here. Okay, if 0 is going here, that means what will be the output? If any of the input is 0, that means the output is 1 here. So this one is here, and what will be the output? This 0 is the output. So both of the inputs are 1. We are getting 0 here, 0 is feedback here, and the output is 1. The Qn is 1. That means whatever we have assumed D, whatever is the input, the output is the same. Okay, so we can make the characteristic table from this here. The characteristic table, as you can see here, this one, it's very important. Qn plus 1, we can make the equation from here. What will be the Qn plus 1? Look, this the output here, if D equals to 0, if D equals to 0 here, so what will be the output? The output will be 1 here. Okay, so what will be the Qn plus 1? 1 into Qn bar, because this is Qn bar which is going here. So 1 into Qn bar equals to Qn, okay, but we are not getting any value here. So we will solve Qn plus 1 bar. So what will be Qn plus 1 bar? This is 1, this is 1. So basically this is 0 and this Qn is feedback here. So you can see 0 into Qn bar whole bar. So it will be 1. So if we are getting 1, automatically this will be 0 because we are getting the value here. This will be 0. So you can see here. If Qn, the assumed output is 0, the output is 0. It is the same. Okay, if D equals to 0, and if so in both of the cases, as you can see here, Qn plus 1 is 0. So when D equals to 0, what will be Qn plus 1? It is 0 here and it is 0 here. We have solved in the previous slide as well. I have taken the example there. Okay, and if D equals to 1, what the value we have discovered from here? It is 1. You can find if D equals to 1, that means 1 I am applying here, 1 is going here, 0 is going here, right? So what will be Qn plus 1? Because if 1 is going here, 1 is going here, 0 is here, so and it is Qn bar, so 0 into Qn bar will be equal to 1 here. So that means in both of the cases I am getting 1. So if D equals to 1, D equals to 1, what will be the output? Qn plus 1 equals to 1 and Qn plus 1 equals to 1. So that is the characteristic table, and you all know how to find the truth table from the characteristic table. How to find the truth table? We will see D equals to 0, D equals to 0, D equals to 1, D equals to 1. What is the Qn plus 1? If D equals to 0, Qn plus 1 is 0, Qn plus 1 is 0. If D equals to 1, Qn plus 1 is 1. Okay, so this is all about the D flip-flop. So you must know why we use the D flip-flop, delay flip-flop, why it is used. Because if we want to use just the set and the reset state of the SR flip-flop, we will use the D flip-flop. Okay, in the next slide I will cover the T flip-flop or the toggle flip-flop. Thank you.